So as we have said more than once, we're going to study equilibrium a lot this semester. But in order to study equilibrium, we have to start with talking about kinetics, because we defined already kinetics are about reaction rates. And remember, the definition of equilibrium is, you know this, right? When the rate of the forward reaction is equal to the rate of the reverse reaction. So we have said that kinetics is how fast a reaction happens, how fast the reaction proceeds to make product, reactant, whatever. It's about reaction rate. And the rate is a measure of the change in concentration of a reactant or product over time. So we're looking at a change when we're talking about reaction rates. If we look at these little things down here, if I made you count, you would count that there are 40 black dots and 0 red dots. So 40 A molecules, we'll say, and 0 B molecules. If you count again, there are 30 and 10 now, because it's a 1-to-1 ratio. When you lose 10 of these, you're going to gain 10 of those. And then you gain 8 and lose 8, et cetera, and we could keep counting. But the point of what I wanted to say here is that you lost 10 in the beginning, and then you lost 8, and then you lost 6, if I did my math correctly, and then you lost 4, 3, 2. It doesn't matter how many that you lost or gained, because they're going to be the same amount. But the little tick mark on the clock, it's 2 ticks every time. So the same amount of time has passed with each of these little snapshot photos. But you've lost a different amount of stuff and gained a different amount of stuff each time. That's because the reaction rate changes as the reaction is proceeding. It's only when the reaction rate is consistent that you have reached this state of chemical equilibrium. When the rate of the forward is equal to the rate of the reverse and the rate of the reactions forward and reverse are no longer changing, we are at equilibrium. So if we're talking about rates just a little bit so that we can then go into talk about equilibrium, we need to know, how do you measure reaction rates? How do you find reaction rates? Well, it's easiest to look at a change in concentration over a change in time. It's easiest to look at some window unit of time and measure the concentration at that starting time and final time and subtract those two values and find the slope of the line, you know, rise over run slope. Yeah. That's really what we're doing. So when we say the rate of this reaction could be defined as the change in concentration of A over the change in time. This could be one way to describe the rate of this reaction. If I use my little blue stuff up here as an example, remember delta means A concentration final minus A concentration initial over time. I don't need these deltas. I don't know why I put these deltas. Over time final minus time initial. So if I look at my little blue plot, my final A concentration, because it's number of molecules, we'll say number of molecules, but my final A is, we'll say, guesstimate 22, and my initial is 30, and my final time is 20 seconds, and my initial time is 10 seconds. So I can find the rate at which A is disappearing by plugging in these numbers, and I will get negative 8 over 10, which gives me a negative 0.8 molarity per second. I'm running out of space, and I'm not a small writer. I apologize. So we can say A molecules are disappearing at a rate of negative 0.8 molarity per second from in the window of 10 to 20 seconds. That's the rate here. It's not the rate over here at 30 to 40 seconds. That rate is different. But at the 10 to 20 second mark, the rate at which A is disappearing is 0.8 molarity per second. So it works out mathematically to give you a negative, but this equation says the rate of the reaction is negative delta A, delta T. That double negative means that if we were to talk about the rate of the reaction, the rate at which the reaction is progressing at this same 10 to 20 second interval, we would say the rate of the reaction is positive 0.8 molarity per second. Just getting real crowded up here, and I apologize, but it is what it is. So change in concentration over change in time, we can calculate A, the rate at which it's being consumed, and the rate at which it's being consumed should be a negative number. We can calculate the rate of the reaction. The rate of the reaction should always be a positive number. Here it's positive because it's a double negative canceling out to give me a positive. We could also talk about the rate at which B is being produced because B is a product. We'll make that one green. We would write it the same. The rate of the reaction could be described in terms of B. That would be delta B, delta T. And if I look at the same reaction window of 10 to 20 seconds, I'm going to do 20 minus 10 over, or underneath B, let's say it ends at 18, sure, that seems reasonable, and 10, and that's great because it's 1 to 1, my math still works out the same. B is being produced at a rate of 0.8 molarity per second. You with me? Great. So as we said earlier, the stoichiometry of a reaction, the mole ratio balance of the reaction, affects the rate. How do you take that into account when you're doing things like we just did, changing concentration over change in time? Well, 2 moles of A disappear for every mole of B that is produced in this new equation up here. So the rate of the reaction, you have to take that coefficient of A into account. And the way that works is that A is consumed twice as fast as B is produced. So that the rate of the reaction, because the reaction has a coefficient of 1, all reactions always have a coefficient of 1. It's a weird little thing that we'll see again and again, but your reaction is happening half as fast as A is being consumed. Oh, this is really getting murky, children. I'm sorry. But B has a coefficient of 1, so B and the rate of the reaction are equal things, but because of that coefficient of 2, you have to take that into account, and it goes in the denominator. Let me give you a summary. If I have this generic reaction here, the rate of the reaction could be defined as negative, because it's a reactant, 1 over coefficient of A times delta A delta T. Or it could be defined as negative, because it's a reactant, 1 over B, the coefficient, times delta B delta T, delta concentration B over T. Or it could be described as positive, because it's a product, 1 over C, where C is the coefficient, delta C delta T. Or it could be described as 1 over D, where D is the coefficient, delta D delta T. What in the world are we doing with this for? When we talk about the reaction rate could be described in any of these ways. And when we have a problem that says, what's the rate of the reaction when B is being consumed at this rate, and they give you a number, you just pick and choose those two and set them equal to each other. If you were given a question that says, what's the reaction rate of A, that A is being consumed, when D is being produced at this rate, you set those two things equal to each other and solve. That's generic. I need specific. How do I do this? For the following reaction, oxygen gas is disappearing at a rate of this. What's the rate of disappearance of NO2? Well, first, I'm going to write out the whole equation thing that I just wrote on the previous slide in generic form. And I'm going to say the rate of the reaction is, or can be described as, negative 1/4, because it's a reactant, delta NO2, delta T. So far, I'm not even answering the question yet, but I'm writing out what I know. I can describe the rate of reaction in terms of oxygen. That's delta O2, because there's no coefficient. 1 is understood. Delta T. Oh, that's negative. I almost forgot it, but you caught me, right? Yep. Or I could talk about positive 1/2 delta N2O5 delta T. So when this equation question says oxygen is disappearing at this rate, what they're telling you is this variable value right here, but it says the word disappearing, so it's saying this value is negative 0.46 molarity per second. So it's disappearing is how I know to put in that negative at this rate, and that negative just carries down. So it says it's disappearing at this rate. What is the rate of disappearance of NO2? So they're asking us to solve for this blue part given that blue part. So I'm going to set them equal to each other, delta NO2, delta T. And I'm going to put my negative 1/4 out front. So this is just like negative 1/4 x equals 0.046 if I cancel out my negative, right? So really I'm saying 0.046 times negative 4. That's the math that I'm doing. You followed along. I know you did. I got faith. Delta NO2 delta T equals, I have the math somewhere, equals negative 184, negative 0.184, squish it in the corner, molarity per second. If you step back, and it's always a great idea to step back, if you step back and say, is it true that this rate of consumption should be larger than this rate of consumption? The answer is emphatically yes, because there's a 4 out front. If you get a smaller number here, well, it's actually more negative, but if you get a smaller number here, absolute value, it means you did something wrong. So reevaluate, because you know that this one is disappearing faster because it's got the larger coefficient. Okay, we're spending too long. We got to move along. But let me read the next question. At the same instant, what's the rate of N2O5 formation? So they gave us O2 in the question sentence, and now they're asking us for N2O5. So on the next slide, we're going to put N2O5 and O2 set equal to each other and solve for N2O5. I could use my previous results, negative O2, the part A answer that I got, essentially part A, but I trust the number that was given to me in the question a little bit better than I trust myself with math, because I do make math mistakes. So I'm going to use what they gave me, and that's why I'm setting it to O2. So without flipping backwards, I'm pretty sure it was 046 that they gave me, and there's a negative as part of the equation. 1/2 x is what we're solving for. So delta N2O5, that's my x, is equal to 2 times the negative 046. So I get positive 0.92 molarity per second. Not too bad. There are worse things. Adios.